In this problem, we are taking a look at a neighborhood health clinic that has a budget of $600,000 per quarter. The director of the clinic wants to allocate the budget to maximize the number of patient visits. So we're looking here to maximize the number of patients that we can have visit the health clinic, which is given as a function of the number of doctors and the number of nurses given by D and N respectively. Now we have this, this is called a Cobb-Douglas model. This is not just some contrived model, but in this case, this model says that the number of visits is equal to 1,000 times D to the 0.6 times N to the 0.3. A doctor gets $4,000 per quarter, nurses get $10,000 per quarter. So our objective is to maximize the number of patient visits. So we'll write that out. We'll just go ahead and say maximize the patient visits. Now, the patient visits formula, or the number of patient visits, is given by this equation here. So we want to maximize V. We want to make V as big as possible, which is calculated by taking 1,000 times D to the 0.6 N to the 0.3. Now, the constraint that we have here, we of course can't just hire infinitely many doctors and infinitely many nurses because we have a budget. So in this case, our budget of $600,000 per quarter is what's going to keep us from hiring more than a fixed number of doctors and nurses. Now, we know a doctor gets $4,000 per quarter and nurses get $10,000 per quarter. So for every nurse that I have, if I were to have 10 doctors, then that would cost me 10 times 40,000. That would be $400,000 of my budget already. But in general, this constraint will be 40,000 D. That's a multiplication there. Notice that this is in dollars per quarter, and this is in I should say probably dollars per doctor per quarter. Dollars per doctor per quarter. And this right here is the number of doctors. So our units would end up being in dollars per quarter, because that's what time frame we're looking at. And we want to limit that to $600,000. Similarly, for the nurses, we'll have plus how much it costs us to keep the nurses or to hire N nurses. And we want that to, well, be less than or equal to 600,000. But since we want to maximize this, the only way we'll be able to make V as big as possible is to make D and N as large as we possibly can. So let's use up the whole budget. If we use less of the budget, we'll hire fewer doctors and fewer nurses, which will lead to a fewer number of visits that we're allowed to cater to. So this will be 600,000. Now we're ready to solve this problem. In this case, we want to make sure that the partial derivatives of V, so we'll have one with respect to D and one with respect to N, is equal to lambda times the partial derivatives of this with respect to D and N. So in other words, we want the partial with respect to V, the partial of V with respect to D to equal lambda times the partial of, in this case, we'll refer to this thing as G of N of dN. And so remember, we would call this f of xy and we would call this g of xy. But since our variables are not x and y, and in fact, this one's not even called f, it's called v, we'll just stick with the nomenclature that we have here. So this is going to be dg dd. And we also need to make sure that dv dn is equal to lambda times dg dn. And finally, our third equation, because we're going to have three variables, we have dn and lambda, so we need a third equation, and that third equation, as before, is going to be our constraint. All right, and next we need to find these partial derivatives, so we can, again, use Wolfram alpha or use some form of technology, but the partial of this with respect to d will be 600 d to the negative 0.4 n to the 0.3, and that's going to equal lambda times the derivative of this with respect to d, which will be 40,000, The partial of v with respect to n in a similar way will give us 300 d to the 0.6 n to the negative 0.7 equals lambda times the partial of this with respect to n, which will be 10,000. And finally, we'll just right below that our same constraint here. We need to make sure that 40,000 d plus 10,000 n is equal to the full budget. And now we're ready to solve this system. This will give us our optimal solution. And so let's go ahead and process that. And the output of Wolfram alpha in this case produces a solution. So here is our entry, our three equations separated by commas. Finally, we see our solution down here. It is perfectly okay to click approximate form, but in this case, it's only the value of lambda. I'm using L for lambda once again. It's only the value of lambda that is in exact form. We don't really concern ourselves with that value at this time. So our critical point is the point d equals 10 and n equals 20. So in other words, we should hire 10 doctors and 20 nurses in order to fully use up the budget and to maximize the number of patient visits. If we want to know what the number of visits amount to, we could calculate v equals 1,000 times d to the 0.6 times 20 to the 0.3, excuse me. This will be 0.3. Now this doesn't come out to a whole number of visits. In totality, we really can't do more than 9,779 visits, but I'm going to round to 3 decimal places, or to 2 decimal places here, just for the sake of comparing to see whether in fact is this a min. Is this a max and not a min? And so the way we could test this is by looking at our constraint and picking points that are close to 1020 that still produce our required budget, but will calculate the number of visits. So let's, for example, consider hiring 9 doctors, and in that case, how many nurses would we need? Well, we just need to make sure that 40,000 times the number of doctors plus 10,000 times the number of nurses, that equals the $600,000 budget. So I can solve for n here by subtracting this from both sides and then dividing by 10,000. And that will give me n equals 24 nurses. So notice that if we remove a doctor, we can hire 4 additional nurses. Each doctor costs 40,000 per quarter. Each doctor costs, each nurse costs 10,000 per quarter. Each doctor costs 40,000 per quarter. So 1 doctor getting paid is equivalent to 4 nurses getting paid. And I'll also consider the number of doctors being slightly greater than. And so if I increase by 1 doctor, I have to decrease by 4 nurses. From having 10 doctors and 20 nurses, I can now only have 11 doctors and 16 nurses. And again, the reasoning for that is because each additional doctor is going to cost 40,000. So in order to keep the budget the same relative to our critical point, we would need to make sure that our number of nurses goes down by 4. You could also plug it in 40,000 times 11 plus 10,000 times some number of nurses equals $600,000, and you would get n equals 16. So what we want to check at these 2 points is the number of visits. So if I have 9 doctors and 24 nurses, the number of visits will be 10,000. Here I think I used 1,000. Let's see, is it 1,000? Yes, it is 1,000. Excuse me, 1,000 times 9 to the 0.6, 24 to the 0.3, and all I'm looking for here is to see that it's less than the total number of visits I would get if I hired the optimal number of doctors. And so that gives me about 9,696 visits, which is certainly less than our optimal point. And then because hiring 11 doctors and 16 nurses also leads to a smaller, lower number of visits, 9,684, that concludes that this point right here is a maximum. So 9,779.33. Now we could round it to the nearest number of visits because that's clearly bigger than both of them. The only reason I rounded to 2 decimal places was just in case the numbers were really close together and it came down to comparing decimal points. 9,779 visits is the maximum with 10 doctors and 20 nurses. And that concludes our problem.